We're now recording. Let me get the slideshow set up from the current slide. Now, what I do want to talk about before we get started today, several of you have your books now, but I'm taking it, not everybody. Okay. From the bookstore has them, right? They got them. Okay. What's that? Okay. Is there any way you can get it or get access to one or something like that by Thursday?
I'll rent mine. You can look at it for $5 now.
$50 all day.
Okay. So we got a bunch of businessmen in here, don't we? Okay. The reason I'm asking this, we really need to get that first test taken, and I want y'all to tell me when you want it. We could have it the last 30 minutes today. I'd say if we don't have it today, we ought to have it, on Thursday. Say again?
I'll say let's do it today. Well, I just got the book. I'll do it.
Okay.
I think to be fair to the people that know how they look,
Thursday. So is that all right with everybody? Thursday. Okay. Now, second. Okay. Here's the other deal. We're in real good possibility, in fact, almost certain, we'll finish the chapter today. And we do have one more lab in this one, so if we're going to have the test on Thursday, that means we'll go until 3:45 today, then have the lab. The lab's rather short, so y'all will be out of here before 5:45, I'm sure. But that means on Thursday, we are ready for the test on Chapter 2 and the test on Chapter 1. Okay, y'all okay with that? So, Take both of them. Okay, so that means the last hour of Thursday's class will be set aside for test. Say again? No, it's going to be two separate tests. I already got the first one made out, and I have the second one made out but not run off. Huh?
Last time you were talking about if you finish it before, then we can just leave. You're going to be both the test at the same time.
No. What I'll do is give you the first one. You turn that one, then I'll give you the second. Okay, the first test is around 10 questions, but they got multiple parts. So it's something like maybe not quite 20 answers worth, so I grade according to the answers, not you miss a question, it's going to be 10 points off. It's not that, and I give partial credit if you come closer in the ballpark, that kind of stuff. Remember, for both tests, you can have a formula and equation sheet. Anything you want to write down on a piece of paper from Chapter 1, anything you want to write down on a piece of paper from Chapter 2. So you can have those there with you during the test. Okay? And
are your tests based off your PowerPoint or are they based off the book?
okay. Okay. Right. I can't say that every answer is on PowerPoint. I'm pretty sure everything's in the book, but I also try to, even if PowerPoint doesn't hit it, I try to say it in class. Expanding on something. I try to always cover those. I can't say I'll get them all, but I do try to hit them all. Well, that's why I say you do your thing to study on. Do a formula and equation sheet. And,
I just for some reason I thought you had said something about you kind of like gave out like some type of study guide at first.
okay. Well, actually, what I do, as I did in the first chapter, I pointed out the study things in the book, as in Chapter 1, there's there's summary at the end. There's summary of equations. Chapter 1 only had one, but you can maneuver that around in several different ways. It had key terms. It had applying the concepts, which is a great thing. I think the best thing to study for most chapters is applying the concepts. Then there's questions for thought, and the applying the concepts have the answers with them. 44 questions in Chapter 1 with the answers. Questions for thought, and for further analysis. They also have the parallel exercises, and we've done samples of most of those in class, so if you can do those, that's another really good thing to study. And I'll go over the same type of thing for Chapter 2 when we get to the end of that chapter. But the other thing, and this is Terrence, right? Okay. The other thing is the, like I said, the PowerPoints, which you can print off Blackboard or watch off YouTube. Okay. Can't print them off YouTube, I don't think. But if you're in class, that's why I encourage you to be taking notes in class. And when I'm working the examples, you're working them too. That type of thing. And then you do your formula and equation sheet. Anything you want to write down, that's, I think, the best way to study. For me to give that to you, that's really passive. It's not, you're not getting as much out of it as if you write it down. Yeah. Oh, yeah. Okay. I want it more active. Okay. All right. Now, I believe, let's see, are there any? Okay. So let's do a quick run through. We'll go today until 3:45, then do the lab. It won't take a full 2 hours, but I'll give you a full 2 hours to do it. Today's lab, by the way, in case any of you escape and come back, is not going to be this way. It's going to be down in 259. Now, I hope. I haven't been down there at 3:45 to see if there's another class. I don't think there is. If there is another class in there, then I'll make some adjustments to it. But that's where the equipment is. At least one part of it set up to be done down there. The other parts I've got a little bit of things to do because I didn't know if there'd be a class between about an hour or two ago and now. So I couldn't set up everything, but I could set up as far as I could. Okay, so then on Thursday and today, my guess is we'll finish Chapter 2 and start on Chapter 3 before 3:45. Okay? Get as far as we can in Chapter 3. And then on Thursday, we'll go 1:15 to probably 2:45. Is that right? And then have a lab from 2:45. No. Yeah. 2:45 until 4:45, and then have the two tests, starting one at 4:45, and the next one when you finish the first test, or 5:15.
We finish our lab before that time.
You can start the test early if you want to. Yeah.
We turn these previous labs.
Yeah, I'll take labs anytime. Okay. And let me remind you of this. I haven't received any papers yet. In fact, I don't think yes. Okay. Okay. And so you do have, and this is sort of one of those good news, bad news situations again. Okay.
Is it the opposite like it was last time?
Oh, it's exactly on the money like it was last time. Okay. The good news is, sorry to say this, folks, but next week is spring break week. The bad news is we won't have class. Okay. So get over it. All right. All right.
I'll be here.
Huh?
That's my first slide.
Okay. All right. So the thing with that is you're going to have a week that I know you're going to be bored stiff, and that might be a great time to get your papers done. Okay? If you haven't gotten them done already, take advantage of the time at hand.
How did you look into a big one?
Okay. Any person, theory, application, anything such as that has to do with physics, chemistry, anything there.
And turn into whatever we're going to write on, we just need to write that on piece of paper and get it.
That's a good idea to do first to make sure someone else has already chosen that topic. So, sort of first come, first serve on that. Okay.
Yes,
All right. What's that?
Yes, Steve,
I don't have one here. Maybe when we go down to, I can probably, wait.
I'll get a newspaper here.
Oh, you got one? Okay, 'cause I bet you there's some paper in back to Brian's office. All right. What's that? Oh, lucky you. All right. Okay. Okay, well, that's why I say try to get them done early so they don't get all clogged up at the end. Okay. So let's move on. Any questions before we get going? Okay, I believe last time we went through Newton's second law. I thought we got further than this. Okay? Yeah. Yeah, we did this. Okay, we did Newton's third law of motion, right? And I believe this is where we start today. This is where my mark was. Is that where y'all are? Okay? Momentum. Okay. Yeah, here's your football player, right? Okay. They do change pictures. That's why they charge you so much.
Yeah.
Okay. Yeah.
I'll go pad with it, 'cause
Okay. But we did this slide, I think, right? And I think we did a couple of examples on this. Okay? So today we're starting with momentum. Kind of a new topic, and this will be the second half. The first part of the lab today is going to be on Newton's three laws, and we'll go down to 259 to do that one. Okay? The second part of today's lab will be on momentum. Now, speaking of football players, I bet you that's where you've heard people talk about momentum before. This team has gotten momentum in the second half, blah, blah, blah. Yeah. You always hear, what in the world are they talking about? What is momentum? This is around page 46, depending on your edition. Okay. Okay. Yeah, you paid for two guys to have their picture made. Okay. All right. Momentum, an important property closely related to Newton's second law, and I would say also third law. And actually, not too far off from first law, okay? The reason I say all that, now, when Newton wrote his big paper on the three laws of motion, it's called Principia, which is a Latin word, and it's basically the principles of natural science or something like that, okay? That text, back then, they thought that no one spoke Latin. No one has spoken Latin for millennia, okay? Except the Roman Catholic Church used to do the masses in Latin, okay? So the priests knew Latin. But scholars knew Latin. And no matter what country they were from, Newton was from England, others from Germany or France or wherever, they wrote all their scholarly work in Latin. So everyone who was a scholar had to know Latin because that's how they wrote. So he wrote it in Latin. So I don't speak Latin. I don't read Latin. I have never even seen Principia in Latin. But from what I understand, he didn't talk about masses much or forces much or things. What he talked about was quantity of motion. That's the term he used, the quantity of motion. And what did he mean by that? This is what he meant. Linear momentum, which is a product of mass times velocity. Okay? So yeah, masses are important, sure. Velocity is important, sure. But the more important principle is this quantity of motion, which is the product of the mass times velocity. So basically, when he referenced all three of his laws, he's, from my understanding, because I haven't read it in Latin, so I wouldn't know what he was saying, but he referred to all three of those in terms. Notice, remember in the first one, first law of motion, an object that rests stays at rest unless acted on by an unbalanced force, or if it's in motion, it stays in motion at a constant velocity, straight line motion, unless acted on by an unbalanced force. Boy, there's a lot of weasel words in there. If you set it in terms of the quantity of motion, it would go something like this. An object's quantity of motion does not change unless acted on by an outside force. Period. You don't have to say at rest or in motion or constant velocity or anything like that. Its quantity of motion remains unchanged unless acted on by an unbalanced force. Okay? That was the first law. The second law, to change an object's quantity of motion, you have to do an applied force. And the applied force is the rate of change of the quantity of motion. Period. No, anything else. And the third law probably read something like this. When two objects collide or interact, whatever you want to call those, the change of the quantity of motion is equal and opposite. That's it. I mean, it's so much easier to talk about, and that's why I use the term. And I think what he was talking about, say again?
Every action is equal and opposite reaction.
Yeah, and he would say it's the equal and opposite change of motion, change of quantity of motion. Exactly. That was it. Okay. We'll see this as we go through it. Okay. It includes effects of both the motion, that's the velocity, and inertia, that's the mass. Okay. So his quantity of motion, momentum, mass times velocity. Now, in today's lab, I'll explain this when we get there, there's actually two forms of momentum, and I've already introduced one. I snuck in the word linear momentum. And this is linear momentum. There is also angular momentum, or you might call it rotational momentum, but you also have that. That's basically what your flywheel does for you, is maintains the momentum. Do you actually have flywheels, don't you, somewhere in the drive shaft? Yeah, that's what it does. That's maintaining, smoothing out angular momentum. Okay, so that's slightly different, but the same principle. We're talking about linear momentum here. Oh, let's go back. Okay, what's that? It basically smooths things out. When I think of a flywheel, I think of a hay baler. Have y'all ever? Okay. And there's usually that big round, and this is making a little square baler, it's not the great big round. It probably has something like it. But when your power takeoff from your tractor is going back, it's turning a big old wheel, a flywheel. And that keeps, even when little things are happening like jostling and stuff, it keeps the movement fairly steady. That's what a flywheel does. It's maintaining angular momentum, not linear momentum. So, what part of this? I mean, you knew what a flywheel was, or yeah, right? That's not linear. That's angular momentum. Yeah, and that's what it really smooths out the motion. Okay. Okay. Let's look at units of this. What's your unit for mass? SI unit for mass. Second? What someone said? Okay, gram, but SI we actually go up to bigger one. Kilogram, right. Metric would be gram, but SI would be kilogram. How about velocity? What's the SI unit for velocity? Meters per second, exactly. In our lab, we did centimeters per second because we're measuring very short things, but SI would be meters per second. So the unit for momentum would be kilogram meter per second. Now, this is the one Newton used. It would have made sense to me, of course I wasn't around back then to argue the case, to me this is what I would have called a Newton rather than a unit of force. But I wasn't there. Someone much earlier decided to name force after Newton. This doesn't have a name. It's just kilogram meter per second. So when you're talking about momentum, there is another unit. We'll talk about that a little bit later, but most of the time it's kilogram meter per second. It doesn't have its own special unit. Many others do, like forces, force is a kilogram meter per second squared. This is a kilogram meter per second. So they're similar, but not quite the same. Okay? But for force, they named it Newton. For this one, it doesn't have a name. So let's go back to our astronaut and the spacecraft. Remember, we did this very problem when we were doing Newton's third law. That's why I said this pertains just as much to the third law as it does to the second law. Okay? Here, the astronaut with a mass of 60 kilograms pushes on the satellite at 120 kilograms, units for mass. Okay? I think I will. Yeah, that's nice. Too old to do closer. Okay. And after they pushed, we derived this before, we calculated this. The astronaut's velocity was 7.750 meters per second in this direction, and the satellite was 0.375 meters per second in that direction. Oh, and by the way, I forgot to mention this. What kind of quantity is velocity? A vector quantity. How about mass? Scalar quantity, not a vector. But that makes momentum a vector quantity. Just like forces were vector quantities. So some of these things are vectors, some are scalar. They've written this in the scalar form, but these, this, and that are actually vectors. Because you see, the direction really matters here. Okay? The astronaut goes this way, the satellite goes that way. Well, what's the momentum of the astronaut? 60 times 0.75. You want to do that in your head? Kilogram, meter per second. That would be 45. 45.0, because you got three significant digits, kilogram, meter per second. Very good. How about the spaceship? 120 times 0.375. We can't do that in your head. I can. It's also 45.0 kilogram meter per second. What's the difference? Doesn't look like any difference except the directions. Okay? The mass doubled and velocity halved. Exactly. Now, this is an illustration of something we're going to hit in another slide or two, and that's that momentum is conserved. Now, what do we mean by that? Okay. I think I may have used this term earlier about mass. Mass is what they call an invariant. It doesn't vary with the problem. If you got the mass now, you're going to have the mass later. So remember we talked about if you went up in a spaceship and went to the moon or just outer space or somewhere, your weight would change because you're outside the Earth's gravitational field. But your mass would still be your mass, right? It's an invariant. Velocity, you think that's an invariant?
Yeah.
No.
No.
Velocity doesn't change, momentum. Velocity does change, momentum doesn't. What was the momentum of the system before the astronaut pushed on the spacecraft? Mass times velocity
Momentum of what?
of the system, the astronaut and the spacecraft. Before he pushed, they were just sitting there side by side, touching, but not pushing. Zero, because neither one had any velocity relative to the other. Once he pushed, and it started going that way, he started going this way at twice the speed, but he of course had half the mass. Then this was say a minus 45, that was a plus 45. After it, the momentum was still zero, because it's a directed, direction matters. One was plus, one was minus, so therefore the momentum after the interaction was still zero. Exactly, and that's Newton's third law. Okay, so you see all these are tied together very nicely with momentum. Momentum is a conserved quantity. It doesn't change unless there's some outside forces acting on the system. Okay? What's that? No, that's not it. Now is it? No, I push on the desk. The desk pushes on me. Okay, you'll have to dent my finger. Yeah, okay, you got it then. If that's the hit, that's fine. Okay. Or you must have had a little brother and you told your mom, no, he hit me with his face on my fist. No. Right. All right. Now, I thought it was a couple slides ago, later, but here it is right now. The conservation of momentum, what I was just talking about. Here we have a system. Now, with momentum, you talk about systems, the entire system. You don't just talk about one piece of it, the entire system. I take it probably most of you have fired a weapon before, right? Okay. We'll call this a rifle. Rather strange looking with a rifle, but okay. A rifle. And, second? Yeah, it sort of does, but that's not a shot. Okay. That's a bullet, so that's why I call it a rifle. Okay? Now, before you pull the trigger, what's the momentum of the system? Zero, because nothing's moving. Zero velocity. You have mass. You have mass. It has mass. Everything has mass, but zero velocity, so the momentum is zero. Once you pull the trigger, okay, you might say, well, isn't that explosion in the casing of the bullet, isn't that an outside force? No, it's an internal force. It's all within the system, okay? So that's an internal force. You pull the trigger, it hits it. You know, of course, there's gunpowder in there, and gunpowder is an unstable substance. So a little bit of a perturbation, just the pecking on the thing is enough to break down that chemical and have a pretty powerful chemical reaction go on. Fires the bullet out in. So after you pull the trigger, the bullet's flying this way. The gun is stationary, right? No. No, not just the firing pin. Once you pull the trigger, it certainly does. If you ever held it off your shoulder, you have a big bruise, right? Or a dislocated shoulder, okay? It's been known to happen. Okay, momentum, yes. Speed, no. That bullet is moving much faster than the rifle, okay? But the momentum is the opposite direction. That's the conservation of momentum. Because this is the mass of the bullet, which is very, very small. The mass of the rifle, rather large, okay? But the velocity of the bullet, really large. Velocity of the rifle, fairly small. But enough to give you a big... Second? Momentum is the bullet. Absolutely. Just in the opposite direction. Remember? Momentum is the vector. Second? Yeah, exactly. Exactly. Now, I don't know if any of you remember the Vietnam War. You may have read about it when you were young or older or something in a history class. But the Vietnam War was a very different kind of war from what we were used to. People were wandering around through swamps and muddy areas and rice paddies and dense jungle and stuff like that. Different from even the trenches of World War I or the charges on the beaches or whatever it was of World War II. It was a different kind. So they wanted to come out with the standard kind of rifle that they used in the world wars was basically like a carbine. Very powerful rifle, sent a bullet at a pretty high rate of speed, but it was a pretty heavy weapon. Really substantial. Well, if you're tracking around in rice paddies and in dense forests and stuff like that, with the rifle over your head so it doesn't get wet until you corrode it like crazy, the carbine would get to you in no time, okay? So they came out with a much lighter rifle. I can't remember the number, M22, or is that heavy or light? Does anyone know? Yeah, but various ones. I don't remember which numbers they were. But they came up with a lighter weight rifle, okay? What's that? Maybe the M14. I don't remember the numbers. Whichever one I'm talking about, they didn't have for very long. The mass of the gun was lighter, so they could walk through rice paddies and not kill themselves. You know, and stuff. What's that? Yeah. Oh my goodness, did it ever. The velocity of that thing, soldiers started having some real bad problems with their shoulders because it kicked like crazy. So they had to do some other modifications. One of those, they actually slowed down the bullet velocity speed. Well, guess what? You know what you really need that velocity speed for is for long distance. In the woods, you're not going to see that long anyway. You're going to fire real quickly and try to get it. So they had to do some modifications. But because you're absolutely right, the momentum of the rifle equals the momentum of the bullet, just in opposite directions. The total momentum of a group of interacting objects remains the same in the absence of external forces. Now, sure, you've got gravity pulling down on here, but this is right when it leaves the barrel. Before any of those other things have happened, that's what the situation is. And we have lots of applications of this. Collisions. Hopefully you've never been in a car accident, right? Good, okay. Yeah, some of us have. I remember I want to say the first day of college, it was the first weekend I was away at school. Freshman, away in Atlanta, first time. My brother, older brother, 2 years older than me, was just becoming a junior. But neither one of us had a car. But he had a friend who had a car. This is the day before classes were going to start, the weekend before, whatever. Now this really dates me. Easy Rider was playing at the Capri in Atlanta. Okay? Y'all don't even know what Easy Rider is, don't you? Oh, yeah, y'all have to live. Okay. I'm thinking Jack Nicholson, that may have been the first movie he was in. I'm not absolutely certain, but it was. And Peter Fonda, I think, was the other star in it. He was the known star, and Jack Nicholson was the other. It was quite a movie. But Frank Michelle, friend of my brother's, in his Z28, was taking us. We're going to see Easy Rider at the Capri. He didn't know exactly where it was. My brother had a sort of an idea. I was in the back seat, right in front of sitting almost on the rear wheel, pretty cramped little condition there. But Frank was tooling along. He always drove too fast. Mike was looking for the theater. That's my brother. And then Mike said, "Oh, there it is. Turn here." So Frank turned there without thinking to look to see if there's anyone coming down the lane he was turning across, which there was. They slammed on brakes. Frank wasn't moving fast enough to get out of there in time, got hit just behind where I was sitting. What a way to start college. I thought, am I going to live to see it? Well, it wasn't that bad, huh? Not all the way. It wasn't that bad, but it was just a shock, okay? And what was the policeman doing? Took his tape measure out there and was measuring the skid marks of that car. Why was he doing that? Say again? Yes, exactly. Using momentum. He could estimate the mass of the car. He knew what brand it was and stuff like this. Look it up on the table, find out the approximate mass to estimate the velocity. Of course, he couldn't tell exactly because it hit us before it stopped, and he had to do a thing for road conditions and stuff. But yeah, that's exactly what he was doing, conservation of momentum. And every time that there's an accident like that, you'll see them out there either stepping it off or marking it off or something and they're using conservation of momentum. Whether they know that or not, that's what they're using, okay? So collisions use this, analyzing any kind of action-reaction. Which law is that? Second? Third law, action-reaction, okay? Interactions, okay? Lots of other applications for momentum, okay? So, Wes actually, the other day, was it this class? I don't think it was. I was moving the chair and didn't know that the handle here, it caught under there. I moved the chair and pulled the computer off. I thought, I bought a new computer, but fortunately it was shock tested, so it was okay. All right, so let's do example 2.14. There's just no room on that slide. Here, we'll do it here. All right. 2.14. A 20,000 kilogram railroad car. Okay? And I don't draw railroad cars too well, so get over it. Okay? Oh, wait a minute. Let me see. Can I do better? No, I can't. All right. So here's a rail car. Really fancy looking rail car. Okay. And it has a coupler on it. Okay? It's a 20,000 kilogram. What's that a measure of? Mass. That's the mass of the rail car. Okay? Is coasting at 3 meters per second. What's that a measure of? 3 meters per second. That's the velocity. Okay? When it collides and couples with a second identical car at rest. So if it's identical car, that means it's also basically that ugly shape on the same ugly wheels with the same ugly coupler here. And identical would mean, what was its mass? 20,000 kilograms. At rest, what's its velocity? 0. Okay, that's the initial velocity of rail cars 2. Okay, now 20 kilograms. Okay, I think we got the picture here. Okay, prior to the collision, what is the momentum of that system? Second? Mass times velocity. This one has, that one has 0, but this one has, momentum would be, mass times velocity, what would that be? A little louder?
20,000 kilograms.
No, that's velocity, that's kilogram, that's mass, 3 meters per second, mass times velocity, 60,000 kilogram meters per second. So momentum, we'll call this car 1, car 2, okay? Momentum of car 1 initially, is 60,000 kilogram meter per second, okay? Initial momentum of car 1, initial momentum of car 2 is 0, so initial momentum of the system is that. You add them together. Okay, so this is also initial momentum of the system. Okay, system momentum. After the collision, the question is, what is the resulting speed of the combined cars? So we're looking for V final. We got V initial for car 1, and we got V initial for car 2. What we want is the final momentum of the system. Oh, how can we do that? Well, guess what? This is the initial momentum of the system. There's no external forces. Just coupling with the other car is not an external force. So therefore, momentum is conserved. Whatever it is at the beginning, it is at the end. So this is also the final momentum of the system. Well, what is the final momentum of the system according to the equation? What would that be? It would be mass of the system times final velocity of the system. Okay? Which is what we're looking for. This is the unknown. Okay? Do we know the final momentum of the system, Same as the initial momentum of the system. Do we know the final mass of the system? Except they couple. Now you add them together. So the mass of the system now is 40,000 kilograms. That's the mass of the system. I can't write, can I? Okay. It's not that funny. Okay. 40,000 kilograms. Okay? So we know the final momentum of the system, we know the final mass of the system, and we're looking for the velocity. Mass times velocity is momentum. What do we do? It's, I know, really ugly. I don't have much room to write. To get this, we divide both sides by 40,000 kilograms. So divide this by 40,000 kilograms. Okay, these cancel out. Okay, your VS, V final of the system, is, well, lucky us, we can divide out all these zeros. 4 zeros there. 6 divided by 4 is 3 halves. Okay, that's what you said. 3 halves, or 1.5. And what units do we have? Kilogram cancels kilogram, meters per second. Yeah, that kind of makes sense. If you have twice the mass, you have half the speed. Sort of like we saw with the astronaut and the thing. Except these are going in the same direction. Everything's going in that direction now. Okay? But it's just going at half the speed because you doubled the mass. Does that make sense? That's how you do conservation of momentum. The key here, whatever your initial momentum was of the whole system, calculate that, then you know what the final momentum of the system is. Okay. Now, another application of this, we have and this would be really miserable to try to calculate, but it really shows you. Have any of you ever played pool? Okay. What's your initial momentum of the system? Is it, you'll play 8 ball, 15 balls in a rack there, all I'm touching, right? Okay, tight, everything, you lift the thing. What's the initial momentum of the system? The cue ball. The mass of the cue ball times the velocity of the cue ball. It's going down the table in that direction at a certain speed. The mass times velocity, that's the initial momentum of the system. As soon as it hits, wherever it hits on that rack of balls, they start going all sorts of places, and it goes sort of all sorts of places. But guess what the final momentum of that system is? Down the table at the mass of the cue ball times the velocity of the cue ball. Because some of these are going this way, but some are going that way. So those momenta cancel out. Some are heading this way, some are that way. Because this one heading that way, the ones going this way are going even faster. Because the momentum of the system is the same. If you were to add all the, and you had them vectorially, all the vectors going in that direction, this direction, that direction, that direction, the components of that, these in those directions would cancel out. These in that direction minus the ones in this direction would equal that momentum of the cue ball. Every time. Can't be anything else. Okay? Conservation of momentum. Say again? Okay, yeah, and that is also conservation of momentum there too. You mean after they've gone all over the place, and when you hit one ball, yeah, whatever the cue ball is going this way, once it hits. Now, if it hits and this ball goes straight and it either stops or comes back, then it's all in line. But if you hit at an angle and this goes this way, the cue ball goes that way, the momentum beforehand is all in the cue ball. Afterwards, you got some momentum this way, some that way. Those cancel out. The momentum going that way, that's what's left. Cue ball has a little bit that way. This ball has a little bit more that way. those add to be exactly what the momentum of the cue ball was to begin with. Okay, then you start introducing angular momentum. Okay, so that does change things a little bit. Okay, but if you're doing linear momentum, and that's going to be a little bit of an issue in the lab, and I'll explain it to you, and you'll actually see a little bit of that. Okay, but yeah, we're talking linear momentum. If the ball's rolling, not skidding across the table, then it's got some angular momentum. So yeah, you got a little of that confusing the issue. Yeah, very similar to bowling. And sometimes, I mean, I've watched some of the, I don't usually watch bowling that much, but sometimes that ball is hardly turning going down the thing, it's skidding across the floor. But, and then it starts turning a little bit. Friction finally takes over. Yeah, you sure do, yeah. Okay. So then you, but it's not a lot of a change, but it is a little bit. Okay. What's that? Oh, friction, yeah.
What if a ball has a different friction, like it's made out of different material, that pool ball is made out of completely different material that you didn't, would that play a really big part in the...
Yeah, I hope they don't set up my pool table that way. Okay. If they do, I'm not taking any bets, okay? None, okay.
If your cue ball was rubber, it'll bounce off the table.
Just like with those train cars, like, I mean, what if one of the wheels that is rolling on the other car is
Stuck.
has more friction than the other?
Yeah, you sure have a problem. But that's actually, believe it or not, that's why they use rail cars. Because actually, the metal on metal is much less friction than tire on the road. I mean, you got to have friction there.
The resistance he's talking about, say the car that you was hitting,
Yeah.
had one of the wheels locked.
Lock.
That
Yeah,
momentum-
you got some real serious issues
that
there.
momentum
Right.
was-
Then you've got an outside force. Yeah, friction is always an outside force, but that's why they use rail cars. Because if you've ever noticed, railroad tracks are just as level as they can make them. So you don't have this kind of thing. So watch, when you're on the road and the rail doing that, you could be doing like this, the rail line is nearby, and you see it's as flat as they can make it. Yeah, because they're trying to minimize that, and then the friction deal too. Those are slick, metal on metal is really pretty low friction, okay? And at least the negative kind of friction anyway. All right. Next concept is that of impulse. Now this is very closely related to momentum. It's a force acting on an object over some time period. So here you've got force, that's kilogram meter per second squared, right? Force, newtons. The object basically has a mass, okay? So that's where the masses come from. The time, you see there's kilogram meter per second squared, so that's a time in it. So you got that kind of a deal going on. Here's how we do that. An impulse produces a change in momentum. In other words, an impulse is the same as a change in momentum. Now, this goes back to Newton's 3 laws. Basically, you're talking about the second law here. Impulse, and how you can give it a symbol if you want to, like I. I'm not sure that's the best one to give. Oh, wait. Sorry. Let's back up a moment here. That's not what I want. Okay. I just realized. Okay. There was an example 215, so let's go back and do this one. Can I erase this okay? Okay. Okay, let's see. Yeah, underneath there? Yeah. We hadn't gotten this far here, but that's fine. We'll do it here. A student and her rowboat have a combined mass of 100 kilograms. So let's get the student rowboat now. Mine are ugly rowboats, by the way. you're not sounding shocked, okay? That hurts, okay? So here's the rowboat, okay? Must be a rowboat, so it has to have paddles here somewhere, but that's beside the point. And she's sitting in here rowing her boat, okay? Okay, y'all are losing points big time. You know that, okay. Okay, I'm just kidding. Okay, a student and a rowboat have a combined mass of 100 kilograms. So here, the total mass of the system here, here's the system. The mass of the system is 100.0 kilograms. Okay? Now, silly her, she stands up in the rowboat. Okay, not a smart move to make. But she tosses a 5 kilogram rock out of the back of the boat. So here's that 5 kilogram rock. So the mass of the rock is 5.0, how many zeros? Just one. No. 5 kilogram rock. Okay? She tosses it out of the back of the boat. Okay? Okay? With a velocity, she gives the velocity. And by the way, the student in a rowboat, standing in the motionless boat. So initially, what do we have here? This is water here, by the way. Okay? Motionless boat. VI of the boat is, initial velocity of the boat is 0 because it's motionless. But she throws this rock with a velocity of 5.0 meters per second. So she's big on 5.0s here, okay? You got it. What is the resultant speed of the boat? So what we're looking for, V final of the boat. Huh? No? Okay. Remember, velocities are not conserved. What is conserved? Second, momentum, which is mass times velocity. So the rock is leaving with a momentum of what? P of the rock, momentum of the rock is what? Yes, mass of the rock times velocity of the rock, okay? We're at the Hard Rock Cafe here, okay. This is 5.0 kilograms times 5.0 meters per second. So the momentum of the rock is 25 kilogram meter per second. So initially, the boat was at rest. Now you've given the momentum that way. The final system must also be at rest. So the momentum of the boat and the gal must be in this direction at what? Momentum final of the boat is 25 kilogram meter per second. Okay? But we don't know the velocity of the boat. That's what we're looking for. That's the unknown here. But we do know the mass of the boat. The mass of the boat. So this will be the mass of the boat times velocity final of the boat. And the mass of the boat is 100.0 kilograms. So divide both sides by that. And your kilograms go out. What does that leave you with? Yes, the final velocity of the boat will be 0.25 meters per second. Not going very fast, but it is moving in that direction. Okay? So let's say she was out there and she lost her oar, her paddle. It went into the water. She has no way to get back, but she does have a rock, 5 kilogram rock. She throws it 5 meters per second. She starts the boat moving to the shore. Huh? No, she had a lot of rocks and the boat weighs more. But no, okay. No, we haven't taken that into account that actually if the system was 100 and she threw a 5 kilogram rock, we really should be using 95. But they didn't do that in the problem, so I didn't.
So that was a battleship shooting one of the big guys.
Yes, and by the way, if you've ever seen that,
It pushes the ship over in the water.
it surely does. Sideways in the water. The USS Arizona and some of those other big battleships, when they were aiming those, what were those?
The USS Alabama.
Alabama, yeah.
Got pictures of all the guns firing off one side.
The whole ship is moving in the opposite direction. Conservation momentum. Always, always. Now, guess what? Believe it or not, water has friction, right? So there is something lost here. We're assuming no friction here. But that water had friction too, but that's so much.
So every one of these problems, we're assuming that space.
Unfortunately, we sort of make that assumption even though it doesn't quite fit. Unless it tells you otherwise, and after a while we will get that. But their answer was also,
Standing on the ground and you throw a football. Why are you gonna fall back?
okay, because your body compensates for that. And if you were standing on a banana peel and did that, you would slide back because you wouldn't have the friction that hold you in place. That's why the football players wear cleats on the shoes, so they can be fixed in place. And yeah, so there are other things happening there. There are external forces, friction being one of the biggest. Okay, and there is friction.
Space floating and you threw something.
Yeah, you would start.
Same speed that
Well, same momentum, not speed, same momentum, and that's it. If you were on that, let's say you're working on this little arm out here, and somehow the arm comes off the spaceship, and it starts drifting off, and it's not tethered to it. How are you ever going to get back? Take a wrench, throw it in the opposite direction, and now you'll have momentum. With no friction, now you'll ultimately make it back to the spaceship. You have to account for your wrench, though. Okay. Okay. Make a cheap wrench. Okay. Not one that you need later. Okay. Dumb example, but yeah, you get the idea. All right. Sorry, I forgot.
You was in space and you threw something with the same mass as you had.
Right.
Y'all
Then-
do it the same
Then the
speed.
two velocities will be the same. Yeah. All right. So we got the ugly boat. With the, I keep hitting the wrong key here. Okay. Wrong one. Nope. That one. Okay. So, an impulse produces a change of momentum. And what I was going to say, let's call that impulse I. That's probably not the best thing. Probably use I for inertia or something like that. But let's just call it I. And that produces a change, delta change, right? Change in momentum, mv. Okay? Now, that's what an impulse is. Change of momentum. Let's think back. Okay. This is a product quantity. Okay. Do you think your mass has changed any? No, it hasn't. It's invariant. So the only thing that really changed is velocity. So you can pull the mass out of the delta because there's no change of this. Well, let's change this to m times delta v. Okay? Is that okay? Now, m times delta v. That's your change of momentum. I really like this one better, but we'll just realize it goes both ways. Okay. Now, can someone tell me what Newton's second law was? Has a simple little formula. Force equal mass times acceleration. Can anyone tell me what an acceleration is? Change of velocity over change of time. Isn't that what acceleration was? Right? Well, what do we have here? A change of impulse, an impulse, change of momentum. If we were to multiply the delta t by both sides of the equation, that gives us force times a change of. So what do we have here? A force acting on an object for some time period t. So force times a time interval is equal to a change of momentum. That is basically how Newton expresses. He didn't say mass times acceleration. He said the time rate of change of its quantity of motion. That's what a force was. Time rate of change of the quantity of motion. Made it much simpler, Didn't have to introduce a new term. Now, what we've done here is multiply both sides of the equation by the delta t, because acceleration was this, and now force times the time interval, that produces a change of momentum. That's an impulse. And this also gives us that other unit we were talking about. Momentum can be mass times velocity, kilogram meter per second, or it could be what's force measured in. Named after Sir Isaac Newton. And time interval? Second. The Newton second. That's another measure for momentum. Either kilogram meter per second or Newton second. Either one. Okay. So let's think of some applications of impulse or changes of momentum. Now, y'all can't remember this. Say that again? Oh, yeah. All the time. Yeah. Exactly. Impulse. I've forgotten that. You're absolutely right. And that's when they're going sort of slowly, but they're using impulse power. Well, not their antimatter engines. Okay. Yeah, we won't go there. Okay. I can remember when I was, as Mr. Roger Corley used to say, old neighbor of ours, a boy child, back way young, but I wasn't that young. I remember this pretty well. We had some type of a Plymouth, and actually that came later. The earliest cars I remember, I don't remember what kind, it was probably a Dodge type product or a Plymouth or something, because that's what my dad used to bought. But it had a metal dashboard. And that metal dashboard came out and curved in like this, so it was almost in itself a projectile. I mean, not quite. I mean, it was hard. And you know what they used to call the passenger seat? The death seat. Because if you're in an accident, at least the driver had a steering column that would sort of collapse a little bit, and things would bend. The passenger had a metal dash or a windshield to go through, and neither one of them were very good prospects. Okay, but I remember that's what the cars were made of. That was before seatbelts. Well, before seatbelts. Way early in your time. And that's what we had. No seatbelts, nothing. Now, the first, and by the way, if you were to hit a tree, okay, going at a reasonable speed, 50 miles an hour, just say, maybe a little more reasonable, call it 60 miles an hour, what is your change of momentum? Pretty drastic, okay? Because you're going, whatever your mass was, going at 60 miles an hour, which is quite a few meters per second, and you hit the tree, which comes to, or a concrete embankment or something like that, you come to a dead stop pretty quickly. Your change of momentum was quite big. Quite big. But the change of momentum is your force times the time interval. That time interval is very small, 1/1000th of a second, because you're hitting a metal dashboard, right? So the force on you and on your head, your chest, or whatever was enormous. Usually immediate death, okay? That's why it was called the death seat. Or very many broken bones, mostly in the spine and stuff, instant paralysis. It was not a pretty sight, okay? Now I remember, this was the Plymouth. I don't remember what kind it was. We bought one. We always bought used cars, by the way, we could afford the new ones. It had, I'm guessing, about a 1/2 inch or so of padding on that metal dashboard, okay? And what?
I got a 70-mile truck.
Yeah, and this is well before 70. Okay. Still no seatbelts, okay? But you had a little bit of cushioned dashboard. So when you hit the tree or the embankment or whatever it was, now it took just a little bit longer to compress that cushioning. But thank goodness it took a little bit. Maybe it's only 100th of a second now. Same change of momentum. You're still going at 60 miles an hour. You still have the same mass. So the same change of momentum. But now if the time interval increases just a little bit, then the force reduces by that much. Increase the time interval by a factor of 10 from 100 thousandths of a second to hundredths of a second. Not very much. It decreases the force by a factor of 10. So rather than 4 million newtons, it would be 400,000 newtons. Yeah, no, whatever it would be, but it decreases it by a factor of 10. All right. Next thing they came out with after padded dashes were, the lap belts. Okay. Now they wouldn't stop you completely from hitting it, but they sure slowed you down. Okay. You still would probably reach the dashboard, but it would slow you down before you got there. So that meant it took even longer for you to reach the dashboard. So now, same change of momentum, same 60 miles an hour, same weight of the car, same weight of you, same weight of everything, mass of you, but the time interval is now maybe 100 times longer because the seatbelt held you back a little bit longer. Well, guess what? Now the force is 100 as great as it was with the padded dash, okay, or the level of the jump.
Now what about the outside of the car? They made the bumpers to
Oh, yeah.
absorb now than
Yeah. I was at a math meeting in Tuscaloosa, not this past year, but year before this, okay, last year, about a month ago last year. And a guy from Mercedes was talking. And it never dawned on me until he gave this illustration. In the old days, when you had chrome bumpers, metal heavy frames, and everything else, basically the only part of the car that would collapse was the canopy. Right? So a lot of people wound up with engines in their gut, and stuff like that because that's where things wound up. He said nowadays cars are built, they collapse everywhere else, but they put the greatest strength around the canopy where the people are. Yeah, they do everything they can to do that. The bumpers are collapsible. Any extra time you can take to absorb the impulse on that rather than on this, time in your favor. Forces go down same proportion as the time interval goes up. What's that? No, you can't. They're still moving, but at least you're trying to increase the time interval before they feel the impact, and that helps them. They're appreciative, I promise you. Okay.
Yeah, the old Cadillac and the old Corvette, both of them have the same force on the impact. The long car would absorb.
Yeah. Yeah. The lighter weight car, you are a bigger portion of that. Yeah. You're absorbing a little bit more of it than it is, yeah. And that's why they made cars heavier back then too, but still, it was pretty bad. So then they put shoulder. In fact, I can remember the cars that you did the seat belt and the shoulder belt. It was two different fasteners, Yeah, I remember those two. You still got one? Fantastic. Yeah, my dad was so bad at doing that, or he would take it and wrap it across them but not connect it. Why? I just don't like it, Not how we always did it, Yeah. he was trying to fool the cops if he was, he thought they had the seatbelt on, but he just had it wrapped around. Dumb move. I hate to say it about my dad, but I think he actually, in his later years, actually was in an accident. From then on, he wore a seatbelt. The way it was supposed to be worn. He said, I can put up with this. I can relearn this, and he did. Okay. So after then the shoulder thing, now finally they have airbags, and that takes even more time. And the longer the time it takes, the less the force. And I think I mentioned to you the hydroplaning accident, the only accident I've really actually been in, except when Frank Michelle cut in front of the car. I was in the car but not driving at the time. But that one, I never even knew it did. But the airbag came out of the steering thing. I didn't feel a thing. Didn't have a single bruise because nothing ever. Of course, I wasn't going that fast, and everyone was sliding, so probably he slid too. But still, increase that time interval, decrease the force. That's the impulse. Now, airbags do that. That's why roller derby people wear pads. That's why football players wear pads. The helmet has padding. Boy, these days, helmets getting a lot of attention because a lot of football players, old football players, retired football players, showing up with a lot of head injuries. They really need, they need some more protection. And there's a lot of technology going into making a pretty dangerous sport a lot safer. But then you also think about, y'all don't remember Muhammad Ali, do you? Okay. You remember him at the Summer Olympics in '96? Huh? 96? Wow. Yeah, don't tell me that. Okay. Yeah. Well, Muhammad Ali was a boxer. Yeah, you remember what it, huh? Yeah, right. But at the Summer Olympics in Atlanta, he lit the torch. Poor guy had Parkinson's so bad. He's dead now, right? But he had just gotten too many blows to the head. Oh yeah.
Their new helmets they're talking about are so great. This article, they bought about 3 of them. They bought one for the quarterback, and one for one of the other receivers, and they bought one for this kid always ended up getting concussions. He got it, they're supposed to be concussion-proof helmets. He got a concussion in it.
Yeah. Well,
Let's get on with it.
there's no such thing as proof, concussion proof, but to minimize it. Yeah.
Yeah. Like a $400 helmet.
Uh-huh.
They're afterwards like, only you get a concussion with one of these helmets.
Yeah, right.
They're supposed to have really good ratings, but he got one.
Yeah. But that's why all the rules are in there now about head, what do they call that? Targeting and those kinds of things. And I can remember when that was almost a matter of course, especially if you had a really good player, the other team would be. You knew it. Yeah. Yeah. All right. Other things, the padding. Actually, it was in the '96 Olympics in Atlanta, which you were not born yet. Okay. Thank you very much. Yeah. But also, there was the Chinese, there were a lot of conflicts with this. They had some mighty young gymnasts, but they said they were all above this age, but they were tiny little girls, okay? They looked like to me. Huh? I'm sorry.
Who was that?
I don't know what their ages were. They claimed to be 14, 16 or something. Oh, China.
Yeah.
So this one was a vaulter. I don't know what you know about the vault. They run down that strip just as fast as they can go. They jump off of a springboard, go up and they're making twists and turns. They come off of a pommel horse and make a few more, and then supposedly land and stick the landing. That's what the whole deal is. And she was flying down that thing and hit something a little off somewhere, the springboard or the pommel horse or a twist something, and she wound up landing over here, not here. And if you notice in the gymnastics, padding all over those floors. Why? Increasing the time interval on impact, decreasing the force. She missed the pads. She hit the gym floor. Quadriplegic. Bones could not take that force. A little bit further over, the pad time interval would have been much greater, and the force would have been much less. Look at those high jumpers. They jump off here, they land on some pillows, here. I mean, it's just incredible. The pole vaulters, way up there, coming down, and I mean, they're in a pit full of those foam things. Yeah, right in one place and fly up into the air and push off of that. Not for me. My nephew tried to do that, and he did it. I think he did okay in high school, but he was the only one crazy enough on the team to do it. So he got to went to go to state. Yeah. 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 I think my brother and his wife just didn't tell my mom what he was doing because she would have gone nuts. Okay. But that's impulse. Okay. Can you remember when bridges, and we talked about bumpers, chrome bumpers, hard steel, fixed into the car? Yeah, they weren't going to increase the time at all, okay? But nowadays, everything collapses well around bridges, and in fact, on the interstates, they've gone to putting these little fences there. Yeah, the cables and stuff. Because if someone hits that, increasing the time interval, decreasing the force. Because before, concrete bumpers, bankments there, no time interval much to speak of at all. The forces are incredible. Okay. I think we beat that to death, didn't we? Okay. Let's see. I think they're going to show some of the same formulas I just did. So let me give them room to do so. Yeah, here it is. The force. Here is the definition of force. Probably the way Newton said it. Change of quantity of motion per unit time. He came up with calculus that was it. Okay? Which is change between initial momentum, final momentum over the time interval. If that final was 0, then all that change of momentum over the time, that was the force. Multiply both sides by the time, your change of momentum is equal to your force. Increase the time, decrease the force. Same change of momentum. I don't think their equation shows it as much as one I was using, but that's what it's talking about. Okay? Now, moving on now, there is a momentum experiment described at the top of page 48 in my book anyway. Momentum experiment. Basically, what's that? Centripetal. Okay, we'll get there in a minute. But I was talking about this one on top of the page. Momentum experiment. You may have seen these little things that people have on their desks. We're going to be doing something pretty similar to that in lab today. Second part of the lab. That's going to be our momentum, part of the momentum experiment. All right, so now let's look at forces and circular motion. Now, is circular motion accelerated motion? If you're going at the same speed, are you accelerating? No. Yes, you are. What is acceleration? Huh? Because you're changing direction. Velocity is a vector quantity with direction. Even though your speed stays the same, if you change direction, you're accelerating. Absolutely. This is accelerating motion because the direction is changing. Now, which way are you accelerating? Always toward the What word do you always see there? Put an E in here. Center. Center-seeking acceleration. Centripetal acceleration is always pulling you to the center of the circle. A centripetal force must be acting to push you there. That's why at Talladega or all the racetracks they have those curves banked to push you to the center. Huh? I'm sorry? Yeah, high embankment to push you to the center. Okay? The centrifugal force, you'll hear people talk about that. That's an apparent force. It's not really real. It's what you sense, but it's not what's really happening. The centrifugal force, you think of that pushing you out. There's nothing pushing you out. It's that the car is turning in and pulling you inward. Yeah. What's that? Stay in motion. Yes, exactly. Okay? So there really is no centrifugal force. We talk about it, and that's what a centrifuge does. It spins things really fast, throwing the denser parts out and the less dense in, so you separate blood. You get the red blood cells out here, the plasma in here. That's how they do that kind of stuff. Okay? That's how they separate uranium too, by the way. That's why they were worried that the Saddam Hussein had centrifuges that could produce, weapons-grade uranium. We probably should be worrying about Kim Jong-un or whatever his name is. Okay. Centripetal force ends. Centripetal force. Which one? This one or that one? That's the real force. No. Yes, you always hear about this one. This one's not real, that one is. Center seeking, pushing you to the center. Okay. Now, and what it means if you, okay. I can think of it this way because, all you were boys when you were young, right? I bet you sometime you took a string with a rock on it and swung it around your head or did something like that, right? Yeah, okay, you had real toys, okay. Rub it in here. Okay. Huh? Yeah. But you can imagine doing this even if you didn't really do it. Swing it around, but if it ever slipped out of your hand, did it go in circular motion anymore? No, it just went straight for the window, right? No, just seemed like it did. Okay? After there's no more centripetal force pulling inwards, it goes straight line motion. Okay? Here is the illustration of that. If you're going in circular motion, something has to be pulling you in to change your velocity from here to here. Because velocity is always, if you're moving in this path, velocity is always tangent to the path. The center is perpendicular to that. The radius is perpendicular to that. So something is pulling you in. The centrifugal force is pulling you in to change the velocity from here to there to there to there. If you put those vectors on each other, you see the acceleration is toward the center, always. Okay? Now that's all they say. Shame on them. We also need a formula, and they give you one. So let's back off and put it here. The centripetal acceleration, this one, A sub c, is equal to v squared over r. Now, I don't know if you remember my saying so. I'm sure you do because you were paying close attention. That most of the time, if you have an exponent of 2, you're going to have a coefficient with a 2 in the denominator. Not in this case. This is the one, just about the one and only case you don't have that. And there's kind of a reason for that, but we won't go into it. But anyway, v squared over r. Does that even seem like those units would be right? What are the units? Say again? It's called the centripetal acceleration. V squared over r. Remember the picture? V squared is always this way, radius is that way, perpendicular to it. So what would be the units for velocity? This is just going to be units here. Units for velocity? Meters per second, but you're squaring that. So that would be meters squared per second squared Divide that by, what would radius be measured in? Second? Meters. So this meters cancels one of those out, and guess what you're left with? Meters per second square. That's perfectly good for acceleration. R is radius of the circle, which would be measured in meters or centimeters or whatever. A length measure. SI unit would be meters. That's centripetal acceleration. Acceleration. Yeah, I know, but it's an acceleration. But what kind of acceleration? Centripetal acceleration. So we like to focus on the A part, but the C, sub C tells you what kind of acceleration. Okay. Now, what was your formula for force? Second law. Okay, but let's go back to the old one, the one we did before that. Mass times acceleration. So if you're talking about a centripetal force, you do mass times centripetal acceleration. So this will be mv squared over r. Okay? And that would be your formula for centripetal force. Centripetal force. Okay? Now, those are the two formulas. Let's hit the two examples. A 0.25 kilogram ball. 0.25 kilogram ball. What's that a measure of? Mass of the ball. Fantastic. Okay. Is attached to an end of a string, and the end of the string is 0.5 meter string. So what's that a measure of? That's your radius now. Yes, exactly. Moved in a horizontal circle at 2 meters per second. 2.0 meters per second. That's your velocity. Okay? What is the net force needed to keep the ball in a circular path? So we're looking for a centripetal force. Okay. Yeah, 0.25 kilogram times your 2.0 meters per second squared over 0.5 meters. Okay? So again, a meters, okay, let's do the math. 0.25 kilograms. What's 2 squared? 4.0, but you square your units as well. That becomes meters squared per second squared. And then divide that by 0.5 meters. So this meters takes one of those out. And guess what you got? Kilogram meter per second squared. That's a force. What's another name for that? Kilogram meter. Newton, exactly. Now let's do the math. Now this is pretty easy because 0.25 is 1/4, and 1/4 times 4 would be 1. So all that comes up just being 1 divided by 1/2. That's the same as multiplying by 2, so that would be 2.0 newtons. Now I'm not sure we can get the 0.0 out of there, do they? No, they just say 2 newtons. And here's the reason they don't do the 0.0. Because notice everything else they had 2 digits, but this one they only have 1 significant digit. That 0 isn't significant. It's just in front of the thing. So that's why they round up to 2 digits. Okay. Now, example 2.17, suppose you make the string in that example half as long. So now the string is going to be what? 0.25 meters. Okay? So everything else stays the same, only you divide by 0.25. Well, 0.25 dividing by 0.25 is dividing by 1/4, which is the same as multiplying by 4/1. So that would then get it up to 4 newtons. Okay? And that's, now, this is where they get a little crazy with their units. Okay? Because 0.25 has 2 significant digits, whereas 0.5 only had 1, Now they put a 0.0 there. Come on, get real picky about it. I'm not usually that picky, so you get close to it, you're all right. If you miss the number, huh? Yeah, basically it is, except for significance. No. That means something else. 4 means 4 to the nearest unit. So 3.9 would be 4, 4.2 would be 4 to the nearest unit. But 4.0 means it's 4.09 would be 4.1, not 4.0. So you see, it says you're measuring with more precision than you did in the previous one. That's all it's saying. It's not changing the value much. It's just changing what precision you've got. What's that? Let's see. Yeah, 311. Yeah, why don't we? Okay. We will be ready to move to the next slide, which is Newton's law of gravitation. So that's where we'll begin when we get back. Try to keep it. Oh, that was more than 5 minutes. Sorry. As soon as the projector comes up. Any questions so far? I think this is close to the last section. It is the last section in the chapter. Hopefully we'll finish that just before 3:45.
All this is going to be on the test.
Yeah. This is still chapter 2. It's a pretty long chapter. Yeah. Okay. Now, if we don't finish it today and you want to postpone this till the Tuesday after spring break when you have a lot of time to forget it, I would think you wouldn't want to. So let's try to get through it. Newton's law of gravitation. Gravity is a force. It's an attractive force between all masses. All masses. Okay? Is proportional to, remember our proportionality? Looks like the little fish symbol, the alpha symbol. Proportional to the product of the masses. So we have the gravitational force, F sub g. Again, we put the F first, the force, due to gravity, is proportional to the product of the masses. You always have to have at least 2 masses to have a gravitational force. Proportional to the product of the 2 masses, inversely proportional to the separation distance squared. So inversely proportional, 1 over the separation distance squared. Now, sometimes they'll use d squared or whatever. I'm using r squared. Okay? The inversely proportional to the distance squared. Okay? Well, to get that from a proportionality to an equation, we change the proportionality constant to a equal k. Remember? That's what we did. Equal k. But we don't use the symbol k. They use k for so many things. They actually use the symbol g. Capital G, not little g. Little g we use for the acceleration due to gravity. Capital G is called the universal gravitational constant. Okay? Now, this also explains why little g is 9.8 meters per second squared on the surface of the Earth. And we'll do that in example well, I thought we were going, oh wait, I'm on the wrong page. No wonder I can't find it. Sorry. Example 218. Nope. No, example 2.19. We'll do it then. I usually forget and do it now and then have it sometime later. We'll do it in a bit. Now, this provides the centrifugal force of orbital motion. If you think about it, why do we revolve around the sun? Okay? On the one hand, the sun is enormously massive. So why isn't it pulling us straight to the center and we burned out years ago? Okay, no. Centrifugal force is what's pulling us in, but we have an initial velocity in this direction and the gravitational force is pulling us in. What helps us is we're far enough from the sun, even though it's so massive, that the product of our mass and its mass, huge number, but we're really far from the sun, so it's a big force, but it's not that big, and that's what keeps us in centripetal motion, orbital motion. Now, we're not quite circular, close to it, but not quite. We're slightly elliptical, but all of the planets are, okay? So we'll talk about that a little bit later, but this is that. They're going to, I think, show it for you here, so I'm going to erase mine so you can see their rendition of it. No, not quite. This is showing us in the moon. The moon is traveling around us. Again, not quite in a circular pattern, but in an elliptical pattern, but close enough. But the moon's velocity is that direction, but the gravitational pull is in this direction, and that keeps it in close to a circular orbit, which has it always spinning. In fact, it's always falling to the Earth, but it just has enough speed here, it misses. Okay? And that's really what is happening. That's your centripetal force. Yeah, basically it is. Okay? And it's just, the trouble is, this is an acceleration, that's a velocity, so they're not quite apples, they're not quite the same. But here's what makes it more correct. See, right here, say we move to here, and there would be your velocity then, okay? Well, if you take this vector and move it back to here, okay, then this would be your acceleration, and that is straight toward the Earth, because you have to have them at the same import before you do your addition. But you see, this import is over here, so translate that back, and that gives you acceleration toward the center, always. Okay. Not a good picture, but that's really what's happening. Okay. They sure skip a lot. Okay. So let's pick up what they're skipping. Okay? First we'll do, they have the formula. They didn't print it, but I printed it for you. F is equal to G M1 M2 over D squared. I put R squared, they put D squared. This is distance squared. Example 218 says, what is the force of gravitational attraction between two 60-kilogram, which is 132-pound students? Now, this attraction isn't the opposite of attracting. That's totally something else. This is gravitational attraction only. Okay? So we're looking for the force of gravitation, which would be F sub G, and this is equal to that capital letter G, which is the universal gravitational constant, and they did give it to you up in the paragraph. I should have given it to you when I did, but I'll give it to you now. Okay, I'll fill that in just a second. M1, M2 over, they use D squared, R squared, it doesn't matter what you put there. Just representing the distance. Okay? Now that universal gravitational constant is 6.67. Now, you with the cheap book, okay, this is where you get cheated a little bit. And when I talked with the gal on the phone today, she called right before class, and I said, one thing I was really disappointed in, when they printed the customized edition, they didn't print anything on the front inside cover or the back inside cover. Both of those are very useful. I told her I wanted that printed, okay? But this is the physical constants on front inside cover of your new books. If you got the new book, it's there. Front inside cover, it sure should be. You see physical constants? Just after, no, right? The very first page. Very first page. Absolutely first page. Is that the very first page you got?
Yeah.
Nothing in front of that. And what's on the back side of that? Conversion factors, metric group? No. Oh, yeah. Don't tell me. Okay, turn to the back inside cover and see if you got anything. My word. Okay. Do you have the periodic table on the back inside cover? No. You do? Huh? Okay. Yeah. Or is it table of atomic weights? Okay. You don't have this. Okay. No, you don't have it. I know you don't have it. You have it in chapter 8. You have it in chapter 8. But the physical constants, you just have to find them in the text. I swear. The periodic table, but it's probably not there. Yeah. Yeah. Well, I think so, but it's in chapter 8, so you can find it there. Anyway, here's what it is: universal gravitational constant. By the way, it was first measured experimentally by Henry Cavendish. So if you haven't found the paper topic yet, he might be one if you're interested. In 1798, accepted value today is 6.67 times 10 to the negative 11th. Pretty small number. It's Newton meter squared per kilogram squared. That's the units for it. Okay? Then you multiply that, and they told you the mass of these students were 60 kilograms. 60.0 kilogram. That's one student. The other one was also 60.0 kilograms. They're the same mass, and they're 1 meter apart, so 1.0 meters squared. Which, of course, that's not going to change anything except the unit is going to get squared. So what is that force? If you got a calculator, I suggest you use it. It makes it a whole lot easier, okay? And if you don't have a calculator, be sure you bring one for your test so you don't have to be working it all by hand and likely making more errors. Please bring one for the test on Thursday, okay? So if someone has a calculator, do you know how to enter scientific notation on your calculator? Has anyone got one that doesn't know how to use it? The scientific notation tab. Huh? Yeah, he has so many, okay? Everybody knows how to use scientific. Now, if you're using your phone, I imagine there's a way you can get to scientific notation, but I can't swear I can tell you how to get there. What's that? Yeah, the EE key. That's the one that'll do it. So you type in 6.67. Now, some calculators have an EE key, some have an EXP key. One of those two is probably what you did, and when you press that key, you get a little superscripted number there, right? Okay. Now, if your calculator has a plus-minus key somewhere on it, you press that next. No, I'm sorry. Yeah, okay. Press that next, and then type in 11. That will type in that little superscripted area, right? Okay. Then you do times 60 times 60, and then you don't even have to divide by 1. You know what that is, divided by 1. Okay. But the meter is squared, so this meter squared cancels out that meter squared. The kilogram times kilogram cancels out kilogram squared, and that gives you newtons. How many newtons is that? Okay. Okay. 6.67. Okay, did you do the exponent? Oh, no, don't do the times 10. Okay, start it. Okay, 6.67. Okay, now, that EE key press there. Okay, that gives you your exponent. Okay, let me see your calculator here.
So once you get the exponent, plus or minus, right?
Okay. Boy, what do you use for multiplication?
Yeah, I can't remember what they came up with, but I forgot how to get
Okay.
it.
Be careful.
Oh, there it is. Okay. Let me see. If you press that one, yeah, that gives you a minus there. Now you do the 1 for minus 11. Okay? So that's the first part. So it's times 60. It's the regular times 60. then times 60 again. So it's times this 60 times that 60. So it's this times this times this, and then divided by 1. Yeah, times the 60 here, times 60 here. Huh? Okay. Oh, 3,600. Yeah. Okay, got it. Yeah.
Why
Right
is
here.
that times 10 to the negative 11?
Okay, no, that's what when you did the EE key and did the minus 11, that means times 10 to the minus 11. That's what that does for you. It saves you a lot of punching buttons. Okay. And what's your answer? Okay, let's say that again. 0.0006 zeros. And then a what? 24? Is that what you said?
Yes.
Okay, 24. And that would be newtons. Now let's get that back in scientific notation. You move it 1, 2, 3, 4, 5, 6, 7 places. That's 2.4 times 10 to the minus 7 newtons. You think you're going to sense that? Feel that at all? 2.4, and they actually do 2.40 times 10 to the minus 7 newtons. That's 24 hundred thousandths of a million. Yeah, 100 thousandths of a million of a millionth of a newton. No, you're not. You're not going to feel, no, 24 hundred million of a newton. No, you're not going to feel that or sense it at all. Say again?
What was that an illustration of? Like,
Where did the numbers come from? Wait. Okay, what I did to get it back in scientific notation. Is that what you're? Oh.
I was just asking, like, what? I mean, you plug the numbers in to do that. What is that an illustration of?
Oh, this is how much force, gravitational force between 232 pound students standing 1 meter apart. You're not going to feel that at all. Yeah, I got what you're saying. Back to scientific notation. There's usually a key that does that for you. SCI. I think it's SCI. Engineering, you would do it, it would move the decimal another time or two. Okay. All right, so that's your 2.18. Okay? 2.40 times 10 to the negative 7 newtons. Okay? Now. Say again? Oh, okay. Now, they have an illustration that doesn't show up on the slideshow, but now you got your books. This table, I think it's figure 2.28. The force of gravitational attraction decreases inversely as the square of the distance from the Earth's center. Notice that if you go up and they give you tens of thousands of miles up and how your value of g decreases, or acceleration due to gravity. Your weight doesn't change, your mass doesn't change, but your weight goes down big time. Okay? By the way, Terry Brittany just came in, turned that in, but then she left, I guess. I don't know if she's coming back or not. But anyway, she showed up today. Okay. Now, well, we still have lab to do. So, Earth satellites. Oh, wait, before we get to Earth satellites, let's do 2.19. The surface of the Earth is approximately 6,400 kilometers from the center. 6,400 kilometers from the center. Okay? Now, do we usually use kilometers in our metric units? What do we use? Meters. So how do we get that to meters? Yeah, you do 3 more zeros. So let's use scientific notation and write that as 6.4. That would be 3 zeros, and then 3 more would be times 10 to the 6 meters. That's the radius of the Earth. Radius of the Earth. Okay? Now, if the mass of the Earth is 6.0 times 10 to the 24th kilograms, that's a whole bunch of zeros. 6, comma, 0, 0, 0, comma, 0, 0, 0, comma, 0, 0, 0. 8 sets of those 3 zeros there. That's the mass of the Earth. That's a lot, okay? Is that many kilograms? What is the acceleration due to gravity, g, near the surface? Well, our force due to gravity is this capital G times mass 1 times mass 2. Well, mass 2 here, let's do the mass of the Earth. This will be our mass, mass 1, divided by, and we're on the surface of the Earth, so we're divided by d squared. That's the formula. So we want to combine these three together, and that's what gives us little g. Okay? And this is distance from the center of the Earth. So that's d sub e, or what I call r sub e. So let's do it. This is 6.67, right? Times 10 to the negative 11th. And that would be in kilogram meter, it's in newtons, which is kilogram meter per second squared, times meter squared divided by kilogram squared. That's the unit, Newton meter squared per kilogram squared, times the mass of the Earth, 6.0 times 10 to the 24th kilograms, divided by the radius of the Earth, or distance you are from that, and that would be 6.4 times 10 to the 6th meters squared. All right, pull out your scientific calculators, okay? So let's see what we get. 6.67 EE negative 11. Now, be sure you do your change sign, the plus and minus 11, not the subtraction key. Okay? That's multiplied by 6, you don't have to put the 0, EE 24, and that's divided by 6.4 EE 6, but then that number we square. Okay? Then press equals. Second? Yeah, just square this bottom number here. And so you might want to, before you do divided by, or after you do divided by, put it in parentheses, 6.4 EE6, close parentheses, squared, then hit your equal sign. Try it, see what you get. I'll be messing with the units. Here we have meter squared, there we have meter squared, they're gone. Here we have kilogram squared, and there we have kilograms, so one of those is gone. Here we have a kilogram, there we have a kilogram, so that's gone. So sure enough, we're left with meters per second squared, which would be a unit of acceleration. What number do we get with it? No, it took so long to punch buttons. Okay. And by the way, when I was in Nebraska for grad school, there were a couple of other Southerners I knew up there, and one of them came back telling the story. She had gotten in an elevator and said, punch 7 or something like that. And they said, what? Well, punch 7. And then finally, oh, you mean press 7. I said, you Southerners are really violent. You punch things, we just press them. Never mind. Okay. Oh, hey, I'll shoot it. Yeah, it's not that bad. No, you sure? Okay. All right. 6, 7. All right. 6 point or 6. Yeah. Okay. Then divided by, now open parentheses. Okay. 6.4 6 close parentheses and then square right there. What you get? 9 point, and round that to 1 decimal, 9.8. And guess what that is? 9.8 meters per second squared. What's that? Acceleration due to gravity. This is your mass, there's your force. This is your mass, there's your force, and this is your acceleration due to gravity. 9.8 meters per second squared. That's exactly where that comes from. Okay. Now let's do example 220. Can I erase it? Did you get it? Yeah, I saw that on yours, right? Yeah. Okay. Any questions before I get off of this one? Okay. Example 220. What would be the value of G if Earth were less dense with the same mass but double the radius? Okay. So then we would have 6.67 times 10 to the minus 11. I wish I had kept that up there. Kilogram meter per second squared times meter squared per kilogram squared. Same mass, 6.4 times 10 to the 24, was it? I'm doing from memory, is that right? That was kilograms. I've lost it. There it is, okay? No, that was 6.0 times 10 to the 24. 6.0. But this time we divide by twice the radius, okay? And that would have been, and I'm just going to do it the easy way, double that, and that would have been 12.8 times 10 to the 6th squared. Now that's not really how you do it in scientific notation, but your calculator will still do it. And this would be meters squared. So the meter squared goes out, the meter squared goes out, one of the kilograms goes out, the other kilogram goes out. That gives you meters per second squared. What do you get then? Be sure you square this number. Down here, 12.8. That was doubling 6.4. The number on top is 6, just 6. Okay. I'll put the 6.4 up there by mistake. What you get? Huh? What do you get? 2.4 is exactly right. 2.4 meters per second squared. So in other words, you double the radius because you're squaring that proportional to the separation distance squared. That's 1/4. 1/4 of 9.8, 2.4. So yep, that's it. So our acceleration due to gravity would fall off big time. All right, now we're ready for Earth satellites. Okay, let me get rid of this. Okay. Artificial satellites must travel more than 320 kilometers above the Earth. They've got to, okay? Otherwise, they're not high enough up, they're going to crash. They're going to come falling back down. They must travel at least 8 kilometers per second to maintain orbit, okay? Have to. If they're not, the force due to gravity pulls them down. They spiral down into the Earth. So they, just think of that, 8 kilometers in a second. A kilometer is what? The distance from here to probably exit, let's see, what would a kilometer be? It's less than a mile, 6/10 of a mile, okay? 6/10 of a mile, 8 times that would be 4.8 miles in a second. Okay, that's moving along pretty fast. Yeah, in a second. That's moving pretty fast. Okay. Now, examples of that are GPS. What do we call GPS satellites? What is their orbit? Do anyone know what it's called? Yeah. They have to stay in position. And I think that's called geosynchronous orbit. That's it. Geosynchronous orbit. Meaning they can't move. Okay? If they're above, let's see, this looks like Europe. So let's say this one is above Prague, Czechoslovakia. This one's above somewhere in British, let's say Ontario, Canada. And this one down here is say above Nairobi, Kenya. Okay. That's where they are. They have to stay there because if they're moving, if the Earth's spinning faster than they are or something like that, guess what? They can't tell you except right when they're in the right place where you are because they have to be fixed in geosynchronous orbit, spinning at the same rate as the Earth. Of course, they're a lot further out, so they're spinning faster, but they have to be that way. And you have to have 3 of them. Without 3 of them that you have a signal from, you can't use GPS. Now, you probably have more than 3, but you have to have at least 3. Because if you're looking just at this one on that frequency, and you're not doing this, your thing is, that puts you anywhere on this circle right here. If you had this one and that one, that puts you here or here, where you're either there or there. You have to have the third one. What they call this is, they call this triangulation. You have to have 3 to get you, you're right there. Now, the odds are they're not going to get you there, then they're going to average about where you are. So they're not going to have you precisely. I think most of them say they get you within, 10 meters, 100 meters, or something like that? What's that? Unless you're in the military, and then they have within a few centimeters, maybe. They can say they can actually read license tags or something like that. It's just incredible how precise they can be. Okay? So yeah, this is the commercial GPS. Okay? Those have to be geosynchronous orbits. Okay? There's a little blurb at the top of page 53 called gravity problems. And that's really worth a read. You talk about those astronauts having 0 gravity or being weightless. They're not quite. They have some weight because they're not that far from the Earth, so they do have a little bit of attraction. Now, I was hearing on the radio a tape from one of the Apollo missions, and they actually picked this up. They said, "Whose is that?" And they were talking about something. Someone had defecated, okay, but hadn't caught it, and it was just floating around the cockpit. And if you think about that, that's an enclosed space. Everything that goes in there or comes out there basically stays there. So they sent up a biochemist, a molecular biologist, in one of the last not shuttle missions, but space station missions. I think she's up there now doing lots of experiments because everyone who's been in brings in all the germs they bring in, and none of those get to leave. So that place is filthy, not just from that kind of stuff, from everything they brought in, the clothes and everything. They have whole colonies of bacteria growing everywhere. So she's up there trying to study what's there and clean up, in some sense, what's there. Pretty sickening, isn't it? Okay, there's a blurb in here, people behind the science, Isaac Newton, well worth a read. Now, if you choose to write on Isaac Newton, be sure you get me that title pretty soon, because lots of people like to choose him. This is not a source. This gives you ideas. You have to get your source from outside the book. Okay. There's another concept applied, apparent weightlessness. Again, something that you can do now. Actually, do you know how, and literally this is how they used to, I think they still do, the astronauts initially practiced for weightlessness. They go up in a jet that flies at enormously high altitude, and then they dive extraordinarily rapidly so that they equal, their acceleration downward equals the gravity's acceleration, so then you feel weightless. Of course, sometimes they got to come to a sudden stop and come back up. The astronauts have a nickname for those flights. You know what it is? The vomit comet, because they just about all of them throw up. You know, they make those really sharp pulling, all those G's. Yeah, they lose it. All of them do. In fact, they said John Glenn was notorious for having motion sickness in his cockpit. I can't imagine that close in the spacesuit. You know, yuck. For how many days? Ooh. All right. So apparent weightlessness, another well worth a read. That's the end of the chapter. And I'll say this every chapter. You'll get sick of hearing me, but I'm still going to say it. Nothing replaces reading the chapters. So get your books. You got 2 chapters to read, okay? Read them. But at the end of the chapter, we have a summary. Now, this one I think is a great deal longer. Of course, this was a long chapter, but you still can't get everything in that summary. So after you've read the chapter, that summarizes it pretty well, but I can't even begin to say everything you need to know is there. You need to know the chapter 2. But in the last chapter, 1 equation. In this chapter, 11 equations. And then when you think of all the different ways you could rearrange those equations, that multiplies by 2 or 3 or 4. Okay, so lots of things. On my formula and equation sheet, I'd make sure I had all of those down there. Okay? Then they have key terms. Now this is not that big a key terms list, but it is pretty significant. They put them alphabetically, but they put the page numbers where you can first find them either described or defined. But then they have applying the concepts. And in this chapter, there are 47. In the first chapter, there are 44, so a few more here. But they do have the answers at the end. I can't swear that all the answers are right. Most of them, I think, have been corrected. In the early editions, we usually find several, or a couple every now and then that would be wrong. So that's a great thing to study, especially for the second test. Okay? Questions for thought, not a bad thing to look at. For further analysis, 6 questions there, the 12 and questions for thought, that's probably about normal or maybe a few less, and then for further analysis, that's about normal, maybe a few more, because that's usually not as long. Then you have the parallel exercises, Group A and Group B. Those of you who have the big books, the Group A answers are in the back. Group B are not. But we've done most examples that are similar to these. Those are well worth doing a few of each type. And I think they usually split them by type, so do a few of each type. Okay? Best thing to study for the test. Conceptual questions as multiple choice, that's probably number 1 best. And then probably parallel exercises are next, but all those others are good things to study. Okay, I think we must be, oh yes, we're past time. Let me go on and call the roll the second time so I won't forget to do that again. James is still here. Okay. Terrence is still here. Camp is mostly here, sort of here, a little bit here. Okay, Slim, maybe not much at all, but Slim's here. Dart is here. Mason's still here. Samuel's still here. Ryan's here. Alfred's here. Jeremy didn't make it in today, and I take it he's not going to. Charles is still here. Brittany showed up and disappeared, and Trevor is still here. And by the way, Carrie didn't make it in today. Okay. All right. Now, again, you have a few minutes before we get, I'll go and give you your lab so I don't have to haul them around. They're not very heavy. They're much smaller than the first one and the last one were. And there's not a whole lot of reading you can do ahead of time, but you can get a general idea of what we're going to be looking for. You'll have a couple over. And here. Okay. Pass one back. I'm sorry. The ones I make up are not nearly as long as the one the book makes up. Okay. So what we'll be going, now again for folks, we're going to 259 today. Not down this way, but down the half flight of stairs first. Classroom on the left. Now if there's a class in there, don't go in. Okay?
Going in? Yeah. Okay.
What's that?
We're going in? Okay, I'll go in.
Yeah, I'll get the stuff out that we need out. Okay. Let me turn this in. Okay. And it's going to take me a little bit to get my stuff discombobulated here and moved down there. Thank you. All right, so you got a little time that you can refresh or whatever. Oh, good morning. Huh?
Morning.
Oh, good. Great. Okay. All right. Okay. Oh, goodness. Great. Great topic. Yeah. Perfectly fine. Fantastic. Okay. What's that? No, that's one. All right, I forgot to turn on the computer. Sorry. They just did the first part of the first page of the lab with 100. Now, don't mess with anything, folks. Okay. So I want to be back here before y'all got here. Okay. Yeah. This is a 200-gram mass, and you can read that on the side here. 200-gram mass. Okay. Now, I guess I'll go without plugging this in for now. Okay. Let me just rehash what we did there. I forgot to start the computer back again. They had 100-gram masses on pieces of paper scattered around the lab. They get a real quick pull on the paper horizontally, and most people said the mass stayed in place. What was the property of matter does that demonstrate? Inertia. Okay, now, here we have two masses. Both of these are 200-gram masses hanging by threads here. Okay, I'll need two volunteers. Okay? Okay, wait, don't do anything yet. Okay. Who's the volunteer? You and who's the other volunteer? Okay? Over here. All right. Now, since you volunteered first, do you want to be number one, or do you want it to be number two? You want to be one person, or you want to be another person?
Who do you want to be, James?
Number one. Okay. Don't touch this one yet. No touching that. Okay. What you're going to do is take the string, wrap it around the finger, okay? And then what you're going to do is to a steady pull on the thread. And once it starts pulling, just very slowly increase the pull, increase the pull. Now, what the rest of you are to do is to notice which thread breaks first, the top or the bottom. Any guesses yet?
The top's going to break.
Okay, well, let's see. Do it. You are the volunteer. Wrap it around the finger. And with a very slow pull. Sure enough, it was the top thread broke first.
Watch your toes, by the way.
Okay, you're supposed to have steel toe shoes in this lap. Never mind. Okay, you bent it for me. Never mind. Okay, now wait. Did y'all all record that? Which thread breaks first? Top. Okay, that's B1. Okay, over here, now my work study sheet is really stingy on the thread here. So what you're to do is wrap it around the finger. I don't think you can get it more than once. Okay? Okay, but what you're going to do, I've got to stop it from moving. Okay. Yeah, no, he tied it too short. Okay? With very much slack in the string, complete slack, then give a very quick pull downward. Okay, make sure it's wrapped around your finger. Okay, lots of slack. Okay. Big fat fingers now. Okay.
Can't
All of a sudden, two people. Which one broke then? Bottom. Okay.
That's the same string. You sure that's the
Same
string?
thread. Same thread from the same spool. Okay? Now, using Newton's law of motion explains the difference in the two outcomes. Why did this top thread break first with a slow steady pull, while the bottom thread broke first with the... Okay? Not very far from exactly it. This one, don't use the term weight. Think forces. This one had two forces on it. The bottom string had only your pull. The top string had your pull plus the weight of the thing. The mass is 200 times g, 9.8 meters per second. Well, this is grams, that would be kilograms. But that is, it had more force on the top string than the bottom string. Which law is that? Net force was greater. Which law deals with net force? Okay, and which one was that? Which one of his laws of motion? Okay, the first one is the law of
force. The second one.
the second law. Deal with net force if you have a net force. Okay. Okay. It's like the kid in children's church. Anything the pastor asks, they say Jesus. You know, that's right. Okay. That'll be close enough. Yeah. Okay. All right. So we described what happened on the first one. That was the second law because the net force was greater on the top thread than on the bottom thread. What about here, though? Why did the bottom thread break first here?
Because it's so abrupt. It was a sudden motion on the bottom. It was an
And what does that have to do with it? Sudden motion?
The force was greater.
No.
But it took a lot to move the velocity was greater.
Sudden motion? Sudden motion? What were you dealing with out there?
Sudden motion.
Inertia. Here, the inertia of the mass, and I'm going to use sort of personification terms here, kept the top string from even knowing anything happened because the mass wanted to stay right where it was. Sudden jerk here, not saying anything about the count, but sudden pull here, and the inertia of the mass kept it right there. So this string hardly felt a thing. The bottom string took it off because of the inertia of the mass. And which of the laws deals with the inertia of the mass? The what? First. The first law of motion is also called the law of inertia. Very good. Okay? You think you got them both? So number 3 is actually worth 2. One for this one and one for that. Okay. While y'all are wrapping that up, I'll get set up for the next.
We staying here?
I need you sketch.
Won't be the first time for you, Dark, would it? Yeah, you haven't had something that. I know, right? Like, you just excluded yourself from so many jokes. Never do that. You still got the baby face no matter what.
That's what you use to mix your milkshakes, man.
Okay.
They kick up 60 PSI.
Okay. Okay.
That was copied. That was copied again.
No, that's it. That was just an extra. See, around but this right here is just like entering on word.
Now, I can't believe this has happened. Just Thursday of last week, we had in the lab, we had 4 teams, and each team had one of these large steel balls. And I brought them back here and personally put them in here. Now there's only 3 of them. We've lost one. So, what we do now, and several people pass it around now. 2 of you volunteered before, the others volunteer now. Need 4 people to measure each one of these steel balls. So I'll put 2 here and 2 here. You got 2 scales to measure the mass of these, and you can either use the rolling, you can try to cut them on here if they'll stay, or if you need that, whatever you use, be sure you zero before you measure. Yeah. Did you zero first? All right, 0 first. Okay. Okay, someone be measuring one of those. Y'all must not want to leave today. What you get? 66 grams. Okay, 1 ball, 66 grams. Okay, the second ball is 66 grams. What was yours? 66 grams. 3 66s. Who's going to do the 4th one? Nope, one of them smaller. But the first 3 were the same. The 4 we had before were all the same, but we're missing one now. That's going to take away a fun thing at the end of the lab. What you get? 26 grams. Okay. Second? Can't even tell. Okay, now, what we're going to do, take 2 of these balls that were about 66 grams. What I'm going to do is place 1 large ball stationary on the track. Okay? Now, what I'm going to do, because it's taken me a while to figure out how to make this work the best, I'm going to roll the second ball down the track at approximately 1 meter per second. Now, I don't know what a meter per second is, so I'm going to scoot it along here, and you just imagine that's 1 meter per second. Because the second's pretty short, and the meter's fairly, reasonably long. So you just imagine this is 1 meter per second. Now, what I want you to be doing was noticing what happens to, you can number the balls either way you want to. That one could be 1, this one 2, this could be 1, that one 2. I don't care. You just get how you're going to number them, and you tell me what happens to ball 1, whichever one this is, immediately after collision. So you got to really pay attention to what happens right after the collision. And then what happens to the other ball, ball 2. So what I'd like to have is a ball catcher here. Is anyone qualified? Okay. So I don't want to be destroying my computer there. Okay? Now, can y'all see well enough? Okay, I'll get down here. Can y'all see well enough? Yeah. Now I'm going to try to scoot this along here. You tell me what happens right after the collision to each of the 2 balls. Okay, that would go too far.
It's got a good job for one.
I feel like I say one speed is
I'm not used to doing it from the prone position here. There.
Speed of one went to speed of.
Okay. You love talking in terms of speed, don't you? Not okay, but it is not that. What were you saying? Momentum. The momentum. Look at the title here. The momentum of the first ball went to the second. Now, how do you describe exactly what happened there? What happened to ball one? Just in terms, what happened to us?
Which one?
Which one you want to call one and which two?
1-year-old.
One roll would be one and the other one two. What happened to ball one at the collision?
Slow it way down.
Okay. Did it actually right at the collision stop? It didn't? Are y'all paying attention to it right after? Okay, do it again. Okay? Let's do it again. Notice right at the collision. Ready? Can y'all see?
Yeah, it's like 2 miles. Yeah, they do stop.
It did stop momentarily. Okay? And the second ball, it moved. Took off and moved. Okay? Now, the first ball, though, after it stopped, then it started rolling again, didn't it? It paused just briefly. That was because of rotational inertia. Rotational momentum. The linear momentum had its top, but because it had some rotational, that kicked in then and said, hey, you're supposed to keep going. So that's why. So that's what I was talking about before. Now,
So
if
it
we
wouldn't
had...
rotate, it would have stopped right there. It wouldn't have
Yeah,
moved.
if we had greased these really well, then maybe we wouldn't have had any rotational. It would just slid down. But then it would have been a big nasty mess for me to put up later, so I chose not to grease it. Okay? So we'll live with it. So B, all you do is describe what happened to the two balls. When you get that done, we will go on to C. Everybody got B done, or are you still working? Okay. Okay, yeah, we'll deal with that. Just describe, after the collision, describe the motion of the two balls. That's all it is. Just describe the motion. Don't explain it. One stopped, one moved, okay? Something like that. And if you want to be a little more specific, it moved with almost the same velocity, wherever we can use velocity, as the first ball, or something like that. I'll let you decide. Okay, but you got it, right? Okay. Now, what was the initial momentum of ball one? Which did y'all call ball one? The one I was moving. What was the initial momentum of that ball? I thought that was no, wait. The one that was moving, you said 1 meter per second. 1 meter per second measures what? Velocity. I asked for momentum. What's momentum?
Velocity times.
What's that?
The mass.
Oh, the mass times the velocity. And what would that have been then?
66 grams.
Okay. Oh, and by the way, I forgot to say this. Sorry. Back up at the beginning, when it says the masses of the ball, I wanted you to record that in kilograms, not grams. But you can write it right above it. You wrote down what, 66 grams? How many kilograms is that? 0.066. That's it, exactly. 0.066 kilograms. And the next one would be? 3 out 0.066 kilograms. And the last one would be? Yeah, 0.026 kilograms. Very good. Okay, so with that in mind, what was the initial momentum of ball one?
0.066 kilograms per meter per second.
Kilogram meter per second. That's the unit for momentum. 0.066 kilogram meter per second. Very good. What was the initial momentum of ball two? Zero, because it wasn't moving. Its velocity was zero. Okay? No. 66 measures grams. It's 0.066 kilograms. Kilogram meter per second. That's why I had to go back and change that. .066 times 1, which is .066, but the units are what changed, kilogram meter per second. The number by itself, not adequate. You need units
So
with it.
the momentum ball 2 would be 0 kilograms.
Yeah, you can just put 0 if you wanted to, but you can't put the units. That would be better. What was the initial momentum of the system? This is answer D.
0.066 kilograms.
Yes, and you add the two together, you get .066 kilogram meter per second. Very good. Now, I didn't have room for all these questions, so I'm going to ask you this one. You don't have to write this one down. What appeared to be the final momentum of ball 1? It stopped, so it went to 0. How about the final momentum of ball 2? Roughly .066 kilogram meter per second. So, does it appear that the momentum was conserved? Yes. Now, what did you say? I'm sorry. Yeah, assuming I did that. That's our assumption because we don't have any way to measure that. Okay. Now, this time I'm going to put two large balls in the center of the track, somewhere here. But they need to be touching, and this, for some reason, is very difficult to do. The track is not perfect, and the balls are not perfect, so they tend to move apart. Okay, got it. Now I'm going to roll the third ball toward these two. Any prediction of what's going to happen? This ball is going to stop. The last ball is going to go. That's what you think, huh? Need my ball catcher. Okay, got a little more precision here. Let's see if indeed we get it. Yes, we did. Okay. All right. So you describe what happens to all three balls. Okay? Ball 1, ball 2, ball 3. After the collision. Maybe I should close the door. Okay, everybody got that one?
Now we got to roll some balls together.
Okay. This time I'm going to roll two balls together. I don't think I'll need a ball catcher on this one, but let's see. Now, this is a tough one to do because I need to roll them at the same speed. They already have the same masses, but I'm going to try to roll them at the same speed. The important thing is to notice what happens just after the collision, right? Any predictions?
Start going opposite way.
What? Okay, let's see. Ready? I need you to. What would you say happened?
They went the opposite way.
Okay. Now let's think about that one a little bit. You write down that answer. Okay. Ball 1, ball 2. This is the G part. Only two of you write with the correct hand. Okay. Okay. All right. Yeah. Yeah. So is my wife. Okay. Okay. Everybody got those answers? Let's think about that in a minute. What was the initial momentum of ball 1? 0.66 kilogram meter per second to the left. What's the initial momentum of ball 2?
Same, right.
Except it was going to the right. So what was the initial momentum of the system? And what do you get? What do you get? zero. One was plus, one was minus, they add to zero. They were both moving like crazy, but the total momentum of the system was zero. How about after the collision? What was approximately the momentum of ball 1? 0.066 kilogram meter per second to the momentum is what kind of quantity? Vector quantity, that's to the left, so let's call that negative. The other one was? To the right, same thing. So the final momentum of the system was? Zero. So the momentum did not change. What's that? Oh, no, it's not on the page. I didn't have room to type it. I was trying to keep it down to one page. All right, this time we're going to place one of the large balls on the track. Okay? And take the smaller ball that was less than half the mass of the first one. And I'm going to roll it at about 1 meter per second toward the large ball. Anyone want to make a prediction of what's going to happen now?
Small ball,
Bounce back?
go back where it came from, and that ball gonna move real slow.
Okay, let's see. My goodness.
I think that whole small ball is gonna hurt shitty off.
Dirty literature. Okay. You ready? Nailed it pretty good there, didn't he? You described it? Did everybody see it? Okay. Okay. What's that? What about it? What happened to it? It moved in the opposite direction. No. All right, let's think about that for a minute now. What was the initial momentum of the small ball? 0.026 kilogram meter per second. Momentum is kilogram meter per second. What was the initial momentum of the larger ball? Zero. Okay. Now, after the collision, which one had greater momentum? Okay. Now, that's partly pretty good reasoning there. But here's the thing. What was the momentum of the system after the collision?
After the collision?
Yeah? 0.026 kilogram meter per second to the right. Because that was momentum before. Momentum is conserved. That's momentum afterwards. Is that what the big ball had? No, it had more than that. Because the little ball had negative momentum. And for the sum of these to be 0.026 kilogram meter per second to the right, that means this one had more momentum than that one did, which meant more than that one even had initially. Because that one changed direction. It had a change of momentum that way. This one had a change of momentum this way, which was actually greater than the little ball had to begin with. But because that's a negative, you subtract that from this one to get your 0.026. Does that make sense? Not faster, had more momentum, which is mass times velocity. Remember. So don't think in terms of velocity, think in terms of momentum. Momentum is what conserved, velocity is not. Okay? Now, this time, we're going to put the small ball near the center and roll the large ball toward it. What's going to happen now?
It's gonna snatch them up like an angry mom or a kid. They're gonna both take off.
Okay? He was abused when he was little. Okay.
It still is.
It should be anyway. Okay. No, sorry. Okay. All right.
The impact of small ball is gonna go about the same speed as the big ball, and the big ball is gonna.
They should both keep going that way.
Okay. Okay. Y'all are hitting it really well. It looks well. Let's see what happens. Now, be sure to notice it right after the collision. Things Anybody take that to the right after the collision? Tell me what happened. I might need the ball picture. I don't want my little kid damaged. Okay. Okay.
They both kept going at the same time.
Well, look at it right after the collision. Which one hit your hand first? The little one did. That meant the large one did slow down. Okay? Because it didn't follow it directly. Okay? So, the little one took off. Okay, yeah, large ball slowed but continued moving in the same direction. The small ball really was going fast then. Would you say it had more velocity than the large ball did to begin with? Yeah, it would almost have to have. It depends on the matches and stuff, but I'll let you figure that. Okay. And I wish someone hadn't ripped off the other balls.
Wow.
Because we were do some other demonstrations that were sort of fun, but we just don't have the 3 large balls now, so can't do it anymore. All right. 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Yeah. Exactly 25. If you do 2 on that number 3, B3, be sure you got 2 answers for that one. That's your 25 points. Yeah. Yes, and that transfers all the momentum to the other model. Was this lab too simple, or did it help? Was it okay?
Great.
Okay. But it's way too short. Y'all want it longer, right?
No.
Okay. All right. If you want to turn it in now, you can. You have a week to turn it in. Whatever you like. And by the way, this was lab 4, not lab 3. Some earlier lights, it was a lab 3. Pleasure. All right, sorry I cheated you out of so many minutes of your tuition dollar. Oh my goodness, a whole hour. Man, I owe you big time dollar. Okay, remember on Thursday, we'll start on chapter 3, go for about an hour and a half. Then we'll do the lab if we, okay, here's the caveat. We don't get far enough in chapter 3, we may not have time for the lab, so we may have to just go 2.5 hours, and then we'll have an hour of tests. I'll give you a half hour for test 1 and a half for test 2. If you finish early, you can finish early. All right, good, thank you. Yeah, if you're ready to turn in, I'll take them over. Good deal. Okay, take your time. I'm here till 5:45. So. I'm going to end